I want to talk about in this lecture something called the mean value theorem. A theorem that gets a lot of use in calculus, even though a lot of the times when it's being used, a lot of students aren't aware that it's what is in use, but it is. Mean value theorem gets enough use that it is known by the acronym MVT. So in calculus, you hear them talking about the MVT. That is a reference to the mean value theorem. Before we talk about the mean value theorem, we need to talk about one called Rolle's theorem. Because Rolle's theorem is used to prove the mean value theorem, so it is usually mentioned first. All right. Now, both of these theorems, both Rolle's and the mean value theorem, have conditions that come with them, conditions that have to be met before the theorem is valid, which is the case for most any theorem. There are conditions that have to be satisfied before the theorem can be applied. All right, so for Rolle's theorem, number one, your function f, the one that you're applying it to, is going to need to be continuous on the closed interval from A to B. Secondly, f is going to have to be differentiable on the open interval from A to B. And f of A needs to be equal to f of B. All right, now that part of Rolle's theorem means it can't be used just any time, it can't be used everywhere. Rolle's has to be used on an interval where the function is equal at the two endpoints. All right, but if you've met this criteria, then what can be concluded is that there exists a number C that's an element of this open interval from A to B such that f prime of C is equal to 0. Now, Rolle's isn't really difficult to draw a picture if you want to talk about what's happening. All right, as a matter of fact, there's only a handful of things that could be happening and for you to apply Rolle's theorem. All right, for example, let's say we had a function that started at A, went up, came back down, and again, the function value is equaled out between A and B. All right, well then, this sketch is of a function that is continuous on the closed, differentiable on the open. F of A is equal to f of B. Then the C that they're talking about, the C at which the derivative is equal to 0, would be right here, where the function hits a maximum point. Right? On the other hand, you might have a function that leaves A, goes downward, comes back up to reach B. Again, it is continuous on the closed, it's differentiable on the open, the endpoints are equal, and the C value that they're talking about will be right here, where it hit a minimum. So you could have a function that went up and came back down, function that went down and came back up. You could have a function, sort of a almost trivial case, that didn't go up or down. And therefore, a function like this, the C value in question would be any and every value in between. The theorem says that this C value exists. It doesn't say that it's unique. As a matter of fact, if you had a function that started at A, went down, came up, back down again. Again, just as long as it ended in the same point, differentiable and continuous as required, then the C values, there'd be two of them. You'd have a C1 where the slope was 0. You'd have a C2 where the slope is 0. So again, this theorem doesn't say anything about uniqueness. It only talks about existence. Now again, this limitation of equality at the endpoints makes Rolle's theorem not as useful as some others, but a corollary to Rolle's is the mean value theorem that we want to specifically talk about. All right, the MVT says, number one, your function is continuous on the closed, and since the MVT is a corollary to Rolle's, many of the Rolle's requirements have been met, like f is continuous on the closed, f is differentiable on the open, and it does not require, one difference with the MVT is it does not require the two endpoints to be equal, but since it doesn't require the two endpoints to be equal, the conclusion is different. All right, the conclusion for the mean value theorem says there exists a C that's an element that's basically, that means it's in the interval from A to B, such that f prime of C is equal to f of B minus f of A over B minus A. All right? So here's what the conclusion is telling us. If you look on the left hand of this statement, what you see is the derivative at a point. All right? That is, the derivative at a point represents your instantaneous rate of change, your instantaneous slope. This expression should be very familiar to you all the way back to Algebra 1. This is slope as calculated using two-ordered pairs. So what this is saying is that for a function that meets these criteria, which is a lot of functions, if you talk about, you're just talking about continuous and differentiable, but what it's saying is that a function's instantaneous rate of change at some point has to equal its average rate of change over an interval. Instantaneous slope has to equal average slope at some point. All right? At some point, a function, its instantaneous rate of change has to equal its average rate of change. All right? That would be like saying, if I drove from Abington to Virginia Beach, all right, that is a trip of 400 miles. And let's say I did it in, just to make some numbers, nice round numbers, in 8 hours. All right. If I drive 400 miles in 8 hours, and since distance equals rate times time, therefore my rate would be my distance divided by my time, which is going to be the 400 divided by 8, which is 50. All right. This is telling me that my average speed in my car is 50 miles per hour. Okay. That's my average. Okay. What do we therefore know about the mean value theorem? I know that since I averaged 50 miles per hour, that at some location, at some point, somewhere, sometime, I was doing exactly 50 miles per hour. At some point in time, my average had to equal my instantaneous. If you average 50 miles per hour, then at some point in time, you had to be driving 50 miles per hour. That way you could say, well, if someone else took the whole trip, they drove the 400 miles, and they did it in, let's be crazy here with our numbers, 5 hours. Well, 400 miles divided by 5 hours is an average of 80 miles per hour. Okay, they were averaging 80 miles per hour. Based upon that, could you give that person a speeding ticket? Yes. There is no way you can average 80 miles per hour without having, at some point in time, traveled 80 miles per hour. As a matter of fact, you have to travel faster than 80 and slower than 80 to average 80, is what this is saying. All right, so you could give a speeding ticket to someone based upon the fact that they traveled 400 miles in 5 hours. You know, at some point in time, they had to be doing 80 miles per hour or more. All right. So in this section, some of the problems you're going to see are going to be ones that ask you to find the C value from Rolle's theorem. Verify that Rolle's can be used and to find that C value. All right, so let's do that one time, or maybe more. Maybe we should do it once or more. All right, so let's give that a try. All right, so let's say that my f of x was equal to 5 minus 12x plus 3x squared. And we're interested in the interval from 1 to 3. And putting that into my calculator would be helpful because I'm going to do a little bit of evaluation here, so that won't help, won't be any harm. 5 minus 12x plus 3x squared. All right, it wants you to verify for this one that Rolle's theorem holds and to find the C value that is associated with Rolle's theorem. So here's the way this question should be answered. Number one, f of x is a polynomial. Therefore, it is continuous on that interval, on the closed. Also, f of x is a polynomial. Therefore, differentiable on the open. Okay. Thirdly, f of 1 is equal to, and here's where the calculator is a little bit helpful, f of 1 is equal to negative 4. And f of 3 is equal to negative 4. So therefore, f of 1 equals f of 3, and the conditions of Rolle's holds. All right, therefore, f prime is going to be of x is going to be equal to negative 12 plus a 6x. You take negative 12 plus 6x, you set it equal to 0, and you get 6x equals 12, so x equals 2, and the 2 is definitely in that interval. So the C value that they're looking for is 2. All right, there's in a straightforward fashion how the Rolle's works. Let's do the mean value theorem. Very similar. Very similar. So let's give it a try. Let's say f of x was equal to a 3x squared plus a 2x plus a 5, looking at the interval from negative 1 to 1. Okay, so number 1, remember the criteria for the mean, a little bit different. F of x is a polynomial. Therefore, it is continuous on the closed. F of x is a polynomial. Therefore, it is differentiable on the open. Okay, and we get this next, let me get this function into the calculator. So 3x squared plus a 2x plus a 5. And looking on my table, therefore, f of negative 1 is a 6. F of 1 is a 10. Therefore, f of 1 minus f of negative 1 over 1 minus negative 1 is 10 minus 6 over 2, which is a 4 over 2, which is a 2. All right? F prime of x is a 6x plus a 2. And you take 6x plus 2 and you set it equal to 2, and you get 6x equal 0. So x equals 0. All right? And 0 is in that interval. So 0 is the c value that they're looking for that satisfies that theorem.